Hi everyone, today I would like to talk about one of my recently completed project in pattern recognition class here at University of Florida. In this presentation, I'll be giving an overview of how iris recognition is done based on the algorithms presented by Professor John Dogman, who is one of the pioneers in this research. So let's go in. First of all, let me tell you there are two broad categories for biometric identification. First is behavioral, which includes voice, gait, and handwriting. As you might notice, these are not the unique characteristic that you might find in the human race. Second category is physiological, that includes face, fingerprint, iris, retina, DNA, etc. Among all these characteristics, iris is considered to be the best identifier for biometric identification of any individual. So let's see why. There are basically a number of properties that make iris the best identifier. Iris is externally visible, colored ring around the pupil. Iris is stable throughout life. Unique patterns of iris are not related to genetic factors. So it's very apparent that you might not have the same iris patterns as your parents have, and also even the twins don't have the same iris patterns, as because both right and left eye of an individual one cannot have the same matching iris patterns. The flowery pattern is unique for each individual, and there is a lot of randomness. Why iris recognition? Iris patterns are unique. Iris patterns do not change with age. Non-contact approach, simplicity and ease of implementation. Template size is relatively small, and image encoding and matching is relatively fast according to the algorithm that I'll be discussing further. So this is the overview of the system model. So it begins with image acquisition, then iris localization, followed by normalization, then unwrapping is done, which follows encoding, and the final step is matching, where you compare two iris of two human being, and then you can tell whether these iris are from the same individual or they are from the different one. The first approach which is presented in the algorithm for iris recognition is segmentation. So in segmentation, it basically isolates the actual iris region from the eyelids and the eyelashes, and the method that are used for this proposed principle are half transform and Dogman's integral differential operator, and there is a very big trade-off between these two methods. In half transform, it's very time efficient, but the segmentation done is not that quite good, as you might notice in the Dogman's integral differential operator. But on the other side, Dogman's operator doesn't give you a very time efficient algorithm for segmentation. There were some problems that I faced during implementing this segmentation part in my software for iris recognition. First one is orientation of the eye image. So if you don't click your picture with a face-to-face orientation, then you might not have the good segmentation. And again, you might want to focus on the contrast level between the iris and pupil, because that also is a crucial factor. Most work that is done on iris segmentation is kind of a variation which is already done in Weil's approach. It detects edge in the eye image and then applies a circular half transform to find the circular pupil and iris boundaries. In the half transform method, circular half transform is used to deduce radius and center coordinates of the pupil and iris region, and the another parabolic half transform is used to deduce eyelids. There are also some problems that I mentioned before. First of all, the segmentation that it gives you might not be perfect, but it's time efficient. and as you might notice that it's very computationally expensive due to its brute force nature, and it may not be suitable for real-time applications. Dogman's method is quite time inefficient, but it gives you a good segmentation of the captured digital eye images. It basically locates the iris and pupil region along with the border of the iris. In the expression, IXY stands for the image which contains an eye. G sigma R is the Gaussian function used over the radius of the iris which is captured. It basically show a local maximum due to the local change of image intensity, which depends on the radius and the center position of the circular contour, which is used for modeling limbus and pupil. So basically localization, which is also referred to as segmentation, is divided into 4 levels. First is separation of pupil from region from eye image. Second, determination of pupil coordinates. Third is determination of iris edges based on previously discussed principles. And the last one is removing the unwanted parts like eyelids, eyelashes, and getting the segmented part of the image. The image that is segmented you can see here. Now the second category comes as normalization. It produces iris region by nullifying the effects of dimensional inconsistency. It basically transforms your segmented part of the iris into a fixed dimension rectangular block. It basically involves converting your Cartesian coordinates to polar coordinates, mapping of each of the iris coordinates into the polar grid using linear interpolation, separating only the annular iris ring, thus eliminating pupil and other regions. Here is the image for normalization. Normalization use Dogman's rubber sheet model, and in this model it's basically mapping each iris pixel onto the polar coordinates, and it essentially look for a circular path and tracks maximum change in the pixel values by varying radius and center position of the circular contour. Here again R and theta represents your polar coordinates, whereas x and y represents your Cartesian coordinates. XP and YP are the coordinates for pupil, and XL, YL stands for the coordinates of iris. Third stage is feature extraction, which is basically helps you in generating unique mathematical templates for iris images, which are nothing but the codes. For iris, there are 2 widely used methods for feature extraction. One is Gabor filters, which I have used, and another is Harvard wavelets. The total number of bits in the template that you will be processing while doing this feature extraction, which is by the way also helpful in enhancing the sharpness of your iris image, which is just normalized. So I was telling you total number of bits in the template is twice the normalized image resolution. So if your normalized image resolution is say 1024, then you'll be having twice of that as a number of bits. Based on the feature extraction process, unique iris templates are generated. Here is the one image that I have put in from my software. Fourth stage is matching. So where your algorithm basically reads the templates and the noise mask which are added to it, and they sort of compare the templates with the templates that are stored in the database while training your system. So some design metrics that are available for matching templates are Hamming distance metric, weighted Euclidean distances, Canberra distance metric. I have made use of Hamming distance metric. In the Hamming distance, this was chosen because, as you know, it provides bitwise comparison and it is easy to implement. Having distance basically tells you the difference in the position of bits between the two templates. So basically it compares the iris codes, which are just now I told you, which might have these number of bits if you are using 8-bit grayscale images. And here is the formula for calculating Hamming distance, which basically takes the XOR of two iris codes and perform the AND operation with the mask of both the iris codes, and it divides by the mask of both iris codes. So while performing this algorithm in my software for iris recognition, I observed that less than zero point 0.2, if you are having this if you are getting this much Hamming distance while comparing two templates, then there will be iris match, otherwise there will be not a match. Also, what I observed was normalization was not perfect and some noises goes undetected, due to which threshold, which is what is zero point 0.2, is not good. It should be as large as it is possible. So let's go into the demo part.